you, Florence. Thank you for this nice invitation. Yes, the subject will be extreme value theory, but essentially to show that it can provide a precise meaning to the notion of weak signals. And it can be coupled with machine learning techniques to answer these questions. So first, I'll give a word about the main motivation. It's essentially anomaly detection, supervised or unsupervised. So it's a rather hot topic today, especially in the application. And I will focus on the machine learning view perspective of this problem, meaning that we shall cope with high-dimensional data. And the key concept will be that of angular measure. So it's a notion that describes very well, exhaustively, the extremal dependence between the covariates in the extreme regions. And this object, we shall see, it's an asymptotic object, so it's not directly observable, but you can try to recover it from data. And this will be the main theoretical part, to show that you can control the deviation between the empirical version and the theoretical notion, with pre-asymptotic, of course, data. And these concentration properties, they have nice consequences. In particular, they permit to show that you can slightly modify classification or regression or other unsupervised machine learning algorithm so that they work well, and by well I mean with generalization guarantees. They work well in the extreme regions when the relevant information for the machine learning task is very far away from the center of the mass. You know that in machine learning, deep learning, the statistics that are computed in general, they are standard averages. And here, of course, to deal with extremal the information in the extreme regions, you need to compute more sophisticated statistics. And if I have time, I will discuss also other classic tasks, such as dimensionality reduction, how to recover the hopefully sparse support of the angular measure. And maybe I'll discuss some applications on real data sets. So as I said, the motivation is to give a meaning to that notion of weak signals. And from a machine learning angle, it means that the data, they will be high-dimensional. So in general, in extreme value theory, problems are tackled from modeling, parametric modeling perspective. Here, the data will be high-dimensional, massive as well, meaning that the sample size will be very large. So extremes will become observable. And the idea is to detect some statistical regularity, but not near the average behavior, but in the tails of the distribution. And it has many applications, in particular predictive maintenance or health monitoring. You monitor the functioning of very complex systems with hundreds or thousands of variables. So in my team, we work much in the domain of aeronautics or energy networks. So the idea is to detect or to compute statistics that permits to possibly to predict a future abnormal behavior of a system. So in general, you have no labels. So sometimes you have labels. It's easier. You know that what works very well in machine learning, it's supervised machine learning. But in most situations, you have no labels, and we shall see that in some sense, rarity will replace the labeling of the data. Okay, and the main assumption is that anomalies, they shall correspond to multivariate extreme observations. So they are multivariate of high dimension, and they will be located in the tail of the data set. So anomalies are extreme, but it doesn't mean that extremes are necessarily anomalies. And in particular, in aeronautics, for instance, if you monitor the functioning of an aircraft engine, so if you have to look into it, so false alarms are very expensive. So it's very important to have a very accurate anomaly detection rule. There are also interpretability issues, but I think I will have no time to address that. So an anomaly, you don't need to know much about this, just a common sense. It's a data point that does not conform with the expected behavior. And the expected behavior, it's a local average or the average. So sometimes you have labels, or in other situations you don't. Okay, and the goal of pursued in anomaly detection is to build from data some region. And of course, if a future observation lies in that region, then you claim that the observation is normal. Otherwise, you raise the alarm. You are far from the... So it's rather easy in the univariate setting, because what is abnormal is, in general, it's what is either too large or too small with respect to some central measurements, such as a mean or a median. Okay? But as soon as you are in dimension larger than 2, there is no natural ordering. Okay? And you have to learn the type of deviation. For instance, learn how to project the data set. So there are other approaches, for instance, statistical depth. So it's a classic way in statistics to define an ordering on a multivariate space. But it's rather rigid. As I said here, the point of view is fully non-parametric. So we won't specify an object such as the statistical depth in advance, but just know that there are other popular ways of addressing this issue of defining an order. So I start with the simplest situation, supervised anomaly detection, which is actually, so it means that you have a data set where you have the answers, a label indicating whether the observation is an anomaly or not. So it's just a classification, binary classification. So this is the flagship problem in machine learning, that of pattern recognition. But you have also the more challenging situations where absolutely no labels are available. And you have situations in the middle. Sometimes you have you may have a semi-supervised setting, but I won't discuss that. Okay, just I tease the talk. So we have said that now extremes observations, they are no observable. That was not the case before. In general, extremes were out of sample. So you had to model somehow the distributions. And that's not the point of view of machine learning. It's completely agnostic. In general, you try to avoid the modeling of the distribution of a data set. You learn what you have to learn. So, and you avoid the curse of dimensionality in general. Simply because you focus on a certain task. So in general, these problems, they are M estimation problems. You fit your neural networks by solving an optimization problem. So I won't discuss optimization in that talk, but the point of view is not that of modeling. Nevertheless, you have to pay a certain price, and the notion we shall use is that of regular variation. So here the data, X, they will, we assume that they will lie on the positive hortant of R to the power D. So D is the dimension of the data. Okay, it could be extended. Here we just focus on the right tail of each component. Okay, so we just assume that the support it's the positive hortons, and as I said, the angular measure will be the point of interest of this talk. So we shall deal with angles. So the angle, that's just the vector divided by its norm. The norm can be actually any LP norm or the max norm. For the presentation, I will just consider the L infinity norm, the max norm. And this angular measure will be a finite measure on the intersection of the sphere of a multivariate space and the positive hortons. And our goal will be to build from data an empirical version and to control the uniform deviations between that empirical version and the true empirical measure. We shall see that these empirical measures, this is no surprise, they will be built by means of largest observations, because we are in the extremes, so we shall just use the largest observations, say the k largest observations. And the order of magnitude of these fluctuations will be of order 1 over square root of k, which is actually the parametric rate. But the main novelty compared to usual statistics is that the guarantees here are non-asymptotic. So in machine learning, most of the results, they are of non-asymptotic nature. You have n data, or you use k data, and you want to learn as best as possible using this data. So n is very long, of course. The infinity is very long, in particular near the end. So the machine learners, they prefer to establish non-asymptotic results. And of course, this seems very abstract, but we shall see that there are nice applications of these results, in particular, to guarantee that classification or unsupervised anomaly detection or regression or dimensionality reduction, it works when it is applied in extreme regions. So that's the global objective of this talk. I said I shall start with the supervised setting. So certainly the most documented problem in machine learning is that of binary classification. So supervised, you have a system, for instance, an image X, so high-dimensional object, and there is a label assigned to it. For instance, you try to decide whether a certain object is present or not in the image. So the label is binary, say it's -1 or +1, for instance. And the goal is to build from data a classifier. It's just a mapping from the input space to the output space. So it has to be programmable. So for instance, if this is your neural network, or this is a support vector machine rule. And hopefully, this classifier should be optimal for all possible data. So the goal would be to minimize the probability of error, the probability that the true label assigned to X differs from the prediction. So this is the classification error. This can be reformulated as the expected of a loss, the 0-1 loss. And ideally, you would like to minimize that quantity. So it's a toy problem to determine the solution. This is known as the Bayes classifier. Just to define it, you need the posterior probability, the probability of being 1 given X. Okay? And of course, the best way of predicting just is to predict the likeliest label. Okay? So if eta of X, the posterior probability, is larger than 1/2, you predict positive. Otherwise, you predict negative. Okay? So this is a well-known folklore in machine learning. But you don't know the future data, you don't know the distribution, and you don't want to try to model it. So you rely fully on data. So you have observations, independent copies of your system XY, and you replace the risk by its empirical version. So you just plug the empirical distribution, you replace it, you replace the true distribution with the empirical distribution. So you count the number of errors. Okay, and you try to minimize that, but over a certain class of control complexity. So it depends on the architecture of the neural networks you choose, or maybe you consider ensemble learning rules. There are many possible classes. Okay, and you try to mimic the best classifier on this set large J. So this is your hyperparameter in your machine learning algorithm. And the idea is to compare the risk produced by the machine learning algorithm and the optimal risk. And if you're familiar with statistics, you can decompose it classically into two terms. On the right here, the bias. So of course, if a class large J is rich enough, this is very small. If it contains, for instance, the base classifier, this is 0. And here, as it has in general a very complicated form, so you can program, of course, your classifier, but your neural network, in particular if it's a deep neural network, it's not an explicit function of the data. Okay? The classifier is produced by some optimization algorithm, and you have no closed analytical form. So you have no choice to control this. So you cannot use delta method or classic tricks in statistics to investigate the fluctuations of that quantity. So you focus on the worst case situations. You bound this by the supremum. So to show that machine learning works for future data, you have to control these maximal deviations. Okay, and in general, in the machine learning literature, they are obtained by establishing upper confidence bounds for these maximal deviations. So you try to control the maximal deviations between the empirical risk and the true risk over the function. And of course, you have to make some assumptions, because you want to make no assumptions about the distribution. So in general, you have to stipulate some complexity property for the class J. So historically, this is a combinatorial notion of complexity, Vapnik-Chervolenkis dimensionality. And so I will skip the details. It's also very well known in the domain. And the rate you get is that of the central limit theorem. And this is no surprise, simply because the empirical risk is just the frequency of error. It's an average. So you have a CLT, the law of large number, for these very simple statistics. And this is universal. So it means this is true whatever the distribution of the data. You need no assumption on that. So what makes that work is that, of course, the loss is the loss 0, 1, so everything is bounded. It's much more ugly if you deal with regression, for instance. You need tail assumptions, but it's very classic. Of course, you can look at situations where the learning rate could be faster. You know that Michel Talagrand has received the Abel Prize recently, so he has contributed much to the refinement of these concentration inequalities, in particular to involve the variance in localization properties in these results. And of course, if you are a deep learner, you know that you have to tune your loss, or the 0-1 loss, it's not appropriate for stochastic gradient descent, or for gradient descent. So you have to smooth or possibly convexify the loss so as to design efficient algorithm. But I won't deal with optimization. So in that talk, the algorithm, just it's sort of black box that provides the minimum of the risk. Okay. Of course, if you want to be really exhaustive in that decomposition, you should incorporate the optimization error. Okay, so a few decades ago, n was very small and the statistical error was very large, so we were not very patient with optimization. But now we have big data sets, so n is very large, so 1 over square root of n is very small, so we are very careful with the optimization. But here I neglect this part. So our goal is to try to predict well, for instance, the label classification, but in extreme regions, very far from the mean behavior, from the center of a distribution. Okay, and if you run an algorithm and you evaluate its error on these regions, it's very bad in general. And you just need to write the full probability equation to see that. Okay, here just because the probability of exceeding a large threshold is very small, this term plays almost no role in the quantification of the risk. Okay. So what could be great would be to consider a conditional probability. The probability of error, but given that you have an extreme observations or an observations higher than some threshold t. But you would like the definition, it would be great if it's completely independent from t. So you need some asymptotic version, so the supremum limit of this quantity. This could be the asymptotic risk. Okay. So we would like to have guarantees for this notion of classification risk, for this asymptotic notion. So with my colleagues, we have developed some framework for classification in the extremes. So the idea is simply to learn the classifier using the k largest observations. And as you are using only k data, you expect a learning rate of order 1 over square root of k. So it seems predictable, but actually it requires much effort to show this. But the algorithm is extremely simple. So you have your data sets. We shall see the reason for that, but you need to standardize it. So you have some rank transformation. So here f hat, it's a sort of, so these are the component-wise cumulative distribution marginals. Okay, for each, so the xij here, they are the components of the observation xi. Okay, and here that's just, so there is a 1 over n plus 1, is just that to avoid that this quantity is 0. Okay, but if it's confusing, replace it by 1 over n and you recover the usual empirical cumulative distribution function. So this standardization is known as a unit Pareto transformation. So it's a typical rank transformation because here you don't use anymore the value taken by the coordinate. You're just using its rank. Okay. So you standardize each marginals, and that should be intuitive because if you have, for instance, a coordinate that has a much heavier tail than the other, it means that in the extremes you will see only the coordinate with the heaviest tail. Okay. So the idea is to standardize all the data so that in each direction they go to the infinity at the same rate. So that's really key to make this, transformation. And then once you have transformed the data using this marginal transformation, you just extract the k extremes data. So you have the labels and you have the transform input information. And you solve the optimization problem using this dataset only, and you ignore the norm of the input. You just focus on the angles they form. Okay. So the idea is that at infinity, there are directions where you have more likely blue points than red points. And the idea is to detect, to use that angular information to solve the classification problem. So it's rather natural, and actually it works. If you do this, of course you have to tune K, and this is a recurrent issue in extreme value theory. So you have to select the fraction of extremes you are considering in the estimation or in the learning stage. But if you do this, of course, you completely outperform a naive technique, which would consist of using all the data set. So a word about multivariate non-standard regular variation. So you have a random vector. We have said it takes its values in the positive orthant. Technically, you need to assume continuous margins. So the f of g, g is the xg is the component coordinate number g of a random vector, and you have this Pareto transform version. So 1 over 1 minus Lg of xg. So this is your rescaled observation. Okay, and as I said here, we shall just consider the infinity norm, so the max of the coordinates. I need to introduce the angles, I think I have done that already, and the sphere, so the sphere of the positive orthant. Okay, all the points with norm 1 lying in the positive orthants. And what is this property of multivariate regression? So it's a very classic, so it dates back from the 70s or the 60s. You have a nice book from David Resnick about this. So it claims that if you rescale, so typically here the threshold t tends to infinity. So the probability that your your rescale random vector belongs to t of b with t tending to infinity. If you multiply that probability with t, so of course this term on the right vanishes and that tends to infinity. But there is a limit, and this limit is actually a measure on the orthant, which is referred to as the exponent measure. So that's the definition of multivariate regression, regular variation. So you need to stipulate some asymptotic behavior, but we shall see that here there is nothing like a parametric hypothesis. This class of multivariate regular variation distribution is very, very large. If you have this property, necessarily the exponent measure is homogeneous. Okay, and actually it can be expressed if you make a polar coordinate transformation. Mu can be seen as the tensorial product of a Pareto distribution for the radius and a distribution for the angles, which is known as the angular measure. Sometimes it was called the spectral measure. Okay, and this is because of this homogeneity property. So you have, of course, so the asymptotic distribution is something like this. Okay, and so the norm is distributed as a unit Pareto, as a classic unique Pareto distribution, and the distribution of the angle, okay, is okay. It means that so there is a relationship. Of course, it's completely equivalent to know the exponent measure or the angular measure. Okay, because of course we have said that the angular measure, it's a measure on the set of angles, and it has this form, the ball with max norm. This is the unit ball, it's like this. So you take a subset of angles, okay, and phi of A, that's just the exponent measure of the part of the cone here that is depicted by the extreme angles. Okay, so there is a complete equivalence between the two notions, and so somehow phi of A, this measure, rules the distribution of the angles at infinity. Okay. And so as I said before, that it completely describes the dependent structure in the extremes. If you have points like this, okay, it means that there is some dependent structure between the coordinates. In contrast, if you have data only along the axes, it means that at infinity, in the extremes, you have independence between the coordinates. Okay. So in that case, that's it boils down to looking at univariate distribution. So that's very simple. And here, the goal is to focus on high-dimensional settings. And so the class of angular measure is very general. It can be any finite measure on the sphere. Okay, so it's fully non-parametric. So of course, it will be less, or analysis will be less universal than the classic machine learning theory of for generalization, because the inequality I have stated, the Vapnik-Chervonenkis inequality, requires no assumption about the distribution. But here we shall assume that the distribution of the data, in classification, the class distributions, that of the positives and that of the negatives, they are both multivariate, regularly varying. Okay. So how to estimate phi? Because it gives you an indication of the directions along which the extremes occur. So the idea is just to mimic the Pareto transform. You just replace the cumulative distribution functions by their empirical versions. You count how many points for each coordinate are less than, so here it's x, sorry, this is not an n, this is an x. Okay, there is a mistake. And so it's a plug-in strategy, and you replace xi by vi hat, okay, the transformation using this empirical version. So what makes this complicated is that you need all the training observations to compute the empirical cumulative distribution functions. So now the transform data, they are not independent anymore. They depend on the whole data set. So that's really what is really challenging to study these quantities. But if f hat is close to f, this should work. And just you replace here phi by phi hat. So here, this is a pre-asymptotic version. So t was tending to infinity. It's replaced by n over k. So k is the number of points that are really used in this summation, okay? And for n over k, if you want n over k tend to infinity, you need that k has to tend to infinity, but at a much slower rate than n, okay? So k and n over k should be large simultaneously, okay? I think I have said that before. The choice tuning k is rather, it's a difficult problem in practice. To find a theoretical answer for that question, you need a much more sophisticated hypothesis, in general, a higher order hypothesis. So you need assumptions about the rate at which this convergence occurs. Here we shall avoid this. Okay. And so it was absolutely not known before. So it was not documented at all, the fluctuations of the empirical measure compared to the true measure. There were some attempts in low dimension, in dimension 2, and only asymptotic results. Okay. And I shall explain why it's very challenging to get results like that. So it's very close to the supremum, to the maximal deviations between empirical risk and true risk. So here we have maximal deviations between empirical measure and the true measure. We take here a collection of subsets of the sphere, Borel measurable, of course. So some complexity assumptions should be required. So we have sets of directions, okay? And ideally, we expect the bound to be of order 1 over square root of k, okay? As when both n and k over n and k, when k and k over n are simultaneously, no, when n over k and k are simultaneously large, okay? And so we have no lower bound, but so it's rather tricky to show that this is really optimal, but there is some hope because this is the asymptotic rate in dimension 2. So certainly we cannot do better than that. Okay. If we knew the ideal rank transformations, if we knew the marginals, everything would be easy because there is this version of the Vapnik-Chervonenkis inequality for error events we have proved years ago. So here, this is very much like Vapnik-Chervonenkis inequality, except here you consider sets that are not frequently visited by the data. So P is that probability. Okay. So here, this is an upper confidence bound for the maximal deviation. Okay. And if you set P is equal to k over n, then you get an upper confidence bound for the rescaled probabilities here at that form. Typically, red bound of order 1 over square root of k. So this could be enough to show that, for instance, classification in the extremes, it can be learned at rate 1 over square root of k. If you don't need to make the margin transformations. Okay, but you have to do that. So the V at that transformation is involved. Okay, and so you can re-express the empirical, the angular measure in terms of the exponent measure. So we have said that so C of A is the cone. Okay, remember that that picture. Okay. And if you re-express the empirical angular measure this way, here P of n is just the empirical distribution, but here as the marginal transformation depends on the data, so it's random in the data. So here, rather than some set gamma of A, you have some gamma hat of A, okay, which depends on the data. so which fluctuates as well. So how to control these fluctuations? So the idea, so I will skip the details because it's rather technical, but the idea, sorry, ça marche pas très bien, is to frame your random set here between two deterministic sets, okay? And to stipulate complexity assumptions for the set of angles, okay, the A's, okay, so as to control the complexity of the framing sets. Okay, so the construction was really different, but this idea had been already used by John Einmal some decades ago. And the key is simply the decomposition of the deviation like this. Okay. Here you have some, as in the Vapnik-Shavlenkis inequality, you have a term that is just the stochastic error, the difference between the empirical distribution and the true distribution evaluated at these framing sets. Okay. You have the framing gap, so the exponent measure of the difference between the true framing sets, okay, plus a bias term, because of course what you compute here, your statistics, they are computed by means of non-asymptotic observations, of course. So you need to control the bias. We are not doing that here, but you need a rate in the definition of multivariate regular variations I have explained before. Okay, and the key is to first is to build these framing sets. Okay, so it's there is no surprise. You build them using balls with your the norm you have chosen. Okay, and of course, so epsilon is the radius. So of course, if epsilon tends to 0, the framing gap vanishes. But of course, it's more difficult to control that with high probability. Your set, your random set, is between the two sets, this one and this one. Okay, but by chance you can balance all the terms, all the free terms, so as to get guarantees. So it's a bit ugly because it's technical, and thank me for avoiding the technicalities, but you have to just to observe that the rate is really of order log k divided by square root of k. Okay, so I don't know if the logarithm can be avoided or not. So certainly this is an artifact of the methodology, or maybe there is a deep reason for that. I don't know. But in spite of huge dependence between the observations we have done, okay. Okay. So if you apply this to the problem I have mentioned before, okay. Here you shall try to minimize the empirical version, but of this quantity. Typically, you choose t equal to n over k. Okay, it means that you, after having made the marginal transform, you use only the angles, and you compute the empirical version. You can get a bound for the excess of asymptotic risk, typically of order 1 over square root of k. So maybe a log of k is lacking here. so that was the original goal pursued. Okay, you can so I skip that. I was mentioning anomaly detection, so I will finish with that. So sometimes you have no label, so the goal is also to determine some region in the observation space where future normal observations should belong to. This can be cast also as an optimization problem. So the idea is it has to do with concentration properties. So you need some reference measure. So you need to find a region containing, I don't know, maybe 95% here of the data. And that region should be as small as possible, using some, you measure the size using some reference measure, typically the Lebesgue measure. So this is known as a minimum volume set estimation. So this is a straightforward generalization of the notion of quantile. Okay, and so the idea is to minimize the size or the volume over a collection of regions under the constraints that that region contains a fraction alpha of the mass of the data. Okay, and of course, typically you choose alpha large, and when your observation is in that set, there is no alarm, and okay, so you can show there is no, this is not surprising. These minimum volume sets, they are super level sets of the density of the observations. So of course, the statistical approach would be to try to estimate the density, but of course you face the curse of dimensionality. So the idea is just like for classification, you replace the unknown distribution by the empirical distribution. Okay? And here you need some tolerance level because, of course, the empirical distribution is not the true distribution, but we know that the fluctuations, they are of order 1 over square root of n. Okay? And so you have guarantees that are very similar to those of supervised classification. And in anomaly detection, that's exactly the same thing. But you look at directions in the extremes that are more unusual than the others. Okay? The idea is to determine minimum volume sets, but on the sphere, okay? By solving some optimization problem. So I don't explain how to solve the optimization problem. It's challenging on the sphere, of course, because the topology is a bit more difficult. But the results I have explained provides guarantee that you can recover the minimum volume set at rate 1 over square root of k up to that log term by means of data only. So here, if you have an angle lying in that region, then there is no alarm. Otherwise, and the bounds they are rather sharp. Of course, they can be refined using model selection, but it permits to get a rate of false alarm much lower. Okay, and just to finish, because I think I'm almost done. The same ideas can be applied for many other machine learning tasks, dimensionality reduction in particular. So we like to make sparsity assumptions in statistics and in machine learning. So that angular measure, maybe it has a sparse support. So maybe not all the facets of a positive hortense are visited by the data points. And as you know now that you can estimate it accurately, you can try to recover the groups of coordinates that exhibit some dependent structure. One says that it cannot run everywhere at the same time. It means that combinatorially, you cannot have all subgroups of variables simultaneously large. Okay, you could try to understand which components exhibit some extremal dependence. And exactly the same techniques can permit you to recover these groups, and with the same, of course, orders. So it was very fast, but it has many applications, in particular in environment sciences, because this sparse behavior is frequently observed in the datasets. So if you are interested in both the theory and the applications, here are a few references. But the main message that, yes, it's possible to learn in the extremes. It's a bit technical because you cannot avoid rank transformations, and it implies some complex dependent structure. There are not only standard sample means in machine learning or in statistics. These statistics, the extreme classification risk, for instance, they are L statistics, so they are all complex order statistics. But nevertheless, you can control non-asymptotically their fluctuations, and you can ground algorithmically. Everything is simple. You just standardize using this empirical Pareto transform, and you apply standard machine learning algorithm, but only to the fraction of extreme observations. So that's why I was very fast about algorithm, because it changed nothing. You can reuse all the routines you are familiar with.
Thanks a lot for the presentation. So we have still time for a few questions.
Just a quick question about your work is the infinity norm, like the ball. And if you change the ball, does it affect the transformation or the rate? Like,
it affects. It's not universal. I can extend this to any LP norm.
Okay. But the transformation is the same that you're doing. The transformation is the same, but not the angles. Of course, you will compute. You know, it's all about the geometry. So here I have said nothing really about the complexity assumptions. So in the usual setting, you make assumptions about the geometry of minimum volume set, or the regions where you expect positive observations rather than negatives. Typically, these are assumptions about the shattering coefficients of these classes of sets. Here, you have to, as you are using these framing sets, you have to translate the complexity properties on the subsets of on the sphere to the framing sets, and so it's rather complex. But it works for most, so in the machine learning algorithm in general, you are using hypercubes or maybe ellipsoids or regions that are defined through parametric equations. So just know that it works. But the choice of the norm is really key in showing that. So I'm able to show that it works for the max norm. So all the figures were for the max norm here. But for an arbitrary norm, I don't know, and we don't know yet. So the max norm, it just means that at least one coordinate is very large. To be extreme, at least one coordinate has to be extreme.
Okay, anyway, we can discuss with Stephan at the break after. Thanks again.